that is your intermediate product. Okay, remember, A is your reactant, X is your catalyst. First what happens, one of the reactant is reacting with your catalyst to form some intermediate compound like AX, and then what is the next step, that is your AX, that is intermediate compound AX is going to react with your second reactant, that is your B, and finally the product AB is formed and catalyst X is recovered at the end of the process. Okay, so why it is called intermediate compound formation theory? Because what happens in this process, both reactants are not reacting directly. Okay, the first reactant is reacting with your catalyst, then what happens, after that reaction some intermediate compound is formed, and that intermediate compound is reacting with your second reactant to form the product, and your catalyst X is regenerated at the end of chemical reaction. Okay, and that is why it is known as intermediate compound theory. The second theory, that is very widely accepted theory, let us try to understand that. What is it? You have a modern theory. Okay, what is this modern theory stating in the catalysis field? That is, look here, you have A reactant, you have B reactant, you are adding catalyst. Okay, what forms? ABX, activated surface complex is formed. It means reactants and catalysts together will form an activated surface complex. So your modern theory is basically, you can just summarize the things into the steps. That is your step 1, that states that the adsorption of the reactant molecules on the catalyst surface means what? These A and B are the reactant. Okay, they are getting adsorbed on the surface of this catalyst X, and that results into formation of your activated surface complex. Okay, then the next step is, you can see here, the formation of unstable activated complex means what? Look here, this activated surface complex is highly unstable. Okay, it is highly unstable. So what happens is decomposition of unstable activated complex, and that is why what is going to happen, your A dot B dot X will decompose in the step 2 to form your product AB, and your X catalyst is regenerated at the end. Okay, so you can understand here very clearly that this activated complex is very unstable. Okay, so it will again decompose in the step 3, decomposition is there, and what happens, desorption of stable products formed to release the fresh catalyst. Desorption of the stable products formed will definitely release the fresh catalyst at the end of the chemical reaction, and that is how the modern theory is summarized. Now in the last lectures we will just put up the brief preview on the topics that we have covered in the last lecture. That is, we started with the structure of atom, as you can see here very clearly. That is, first basic concepts we have taken, the atomic structure. There we have seen that number of protons, number of neutrons, all the things. Atomic mass is summation of protons and neutrons in nucleus. Then you can see the total number of protons defines the atomic number. Then we have discussed the cases, k element shells. Your K shell is very near to nucleus, having the lowest energy. Okay, compared to the L shell, compared to the M, compared to the N. So that we have seen. Then the next thing that is we have seen is difference between orbit and orbital. That was a brief thing, that orbit is a fixed circular path around the nucleus in which electron revolves, and your orbital is a 3-dimensional space in which probability of finding electron is maximum. You can designate as k element, then here you can designate as sp, d and f. That we have seen in the short detail. You can see here it is circular in shape, it is available in various shapes, spherical, dumbbell, that are the things that we have discussed. Then we can see here another thing, that is case of the uranium 23592. That is what you have 235, the right hand side top number is always going to indicate your atomic mass, and the below left hand number is going to indicate your atomic number. So what happens when you want to find out the number of neutrons, then you can always write down atomic mass is equal to proton plus neutron. Atomic number always defines number of protons, and hence you can put up the neutrons will be equal to some subtraction of these two numbers, that is mass minus number, that will lead to number of the neutrons. Similar thing for the different uranium atom we have discussed. Then we stated with the very important principle, that was the Aufbau principle of the construction. That is one of the major important role in the chemistry. Now what it states was, the electrons enters into lowest energy orbital first, and then higher energy orbitals are gradually filled. Means what? Look here, 1s orbital is having lowest energy compared to 2s, 2s orbital is having lowest energy compared to 2p, 2p orbital having lowest energy compared to 3s. So these all things we have discussed. Now what happens? Electron is going to first enter into 1s orbital. When this orbital is fully filled, then only it will enter into 2s orbital, then into 2p, then into 3s. Okay, this thing has to be kept in mind. Now after this we have related one concept, that your s orbital electrons can basically take up 2 electrons, your p orbital can take up 6 electrons, your d orbital can take up 10 electrons, your f orbital can take up 14 electrons. Okay, depending on this we have kept in mind, relating with the Aufbau rule, we have started writing the configuration of the different compounds. Let us see that. Your hydrogen having the atomic number 1, you can see here the first orbital is 1s. So I have taken it 1s. Okay, then what happens? 1s is there, atomic number is 1, so I will write as 1s1. In case of helium, what is the number? It is 2, atomic number is 2. So you know that s orbital can take how much electron? Only 2 electrons. So I can write here 1s2. In case of lithium, you can write here again, that is 1s2. Why 1s2? Because your 1s2 orbital is now fully filled. We have to keep the next electron into the next orbital, that is 2s. Okay, so what I have written? 1s2, 2s1. Again this s orbital is having how much capacity? Of 2 electrons. So when we go for beryllium, that is having atomic number 4, you can see here, that is 1s2, 2s2. Now you cannot keep any more electron into 1s and 2s orbital. You have to go to the next case, that is 2p orbital. Look for the boron. We can see here clearly, boron is having atomic number of the 5. So what we can write? This 1s2, 2s2 is now filled. So your fifth electron is going to enter into the 2p orbital, and that's why we have written here 2p1. Okay, carbon is having atomic number 6. So you know that capacity of the p orbital is up to the 6 electrons. So I can keep the 6 electrons in the p orbital, and after that only I am going to change the orbital. So what happens? Your carbon is having 6 atomic numbers. So you can write here 1s2, 2s2, 2p2. Okay, you can count here and tally the things with atomic number. 2 plus 2 4, 4 plus 2 is 6, so it matches here 4, so that there is no mistake done. Now you can look here nitrogen. What happens to nitrogen? You can look here 1s2, 2s2, 2p3. Okay, then you have seen the oxygen 1s2, 2s2, 2p4. Okay, then you have seen the fluorine 1s2, 2s2, 2p5. How many electrons I can keep in p orbital? 6 electrons. So up to 6 case I can go, I can proceed. So look at the neon. Now neon is having very fully filled configuration. Okay, so that's why it is included into the inert gas category. Okay, as it's all the orbitals are completely filled, its fully filled configuration is there, so it is not going to take or give any more electrons to anyone. Now look at the sodium. Sodium is having 11 number. So what happens? If you recollect the rule, Just look here, there was 2p orbital is now filled, we have to go to 3s, then to 3p. So look for the sodium case. You have 1s2, 2s2, 2p6, 3s1, right? This is the thing that is for your sodium. Look for the magnesium. What is there for magnesium? Magnesium is having atomic number of the 12. Okay. So now you can write here 1s2, 2s2, 2p6, 3s2. Okay. Now 3s2 orbital is fully filled. So immediately for the case of aluminium, we will go to the 3p case. So we can write here the above things are remaining same, but we will put your 13th electron will enter into your 3p orbital. Silicon, that is having 14 number. You can write here 1s2, 2s2, 2p6, 3s2, 3p2. Okay. So how much you can proceed? Look here, there is a phosphorus, there is sulfur, there is chlorine, there is argon, and then there is a potassium. So you can go up to the 20 cases by putting the orbital. If you see here, what happens to the p orbital, if you study this case, rest things are remaining same. This is 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. 3p6 is fully filled here. So what happens here? Potassium is going to utilize the 4s orbital, okay, for its configuration, and that is why the 19th electron of the potassium is going to enter into 4s orbital. So we have written it as 4s1, or you can write the another configuration as potassium as argon 18 and 4s1. That will also be the right configuration. You can see here the calcium. The last case, that is for the 20 element. You can write here 1s2, 2s2, 2p6, 3s2, 3p6 and 4s2. Okay, for the case of the calcium. We have also seen that these atomic numbers, based on that you can also write the number configuration. It's very simple. Hydrogen 1, helium 2, then you know that you can write 2, 1. Okay, beryllium 2, 2, boron 2, 3, and you can fill it up to 8. After that you have to use the next shell. Okay, so you can look here, carbon 6, 2, 4, nitrogen 7, 2, 5, and so on. The configurations can be taken up to calcium. Calcium is going to have 2882 configuration. Now what Pauli's rule states, off-bow principle is very important one, and again the Pauli's rule is also one of the important thing in chemistry. That is, the Pauli says that no two electron in an atom can have all four sets of quantum number same. Okay, see here, your N is your principal quantum number, L is your angular quantum number, M is your magnetic quantum number, S is your spin quantum number. So even if you can see here these things are there, even if these three quantum numbers are same, but definitely the fourth quantum number will be always different, that is spin quantum number. So no two electrons in an atom can have all four sets of quantum number same. Okay, that is the rule of the Pauli. Very important concept in case of the atomic structure, that is ionization energy and electron affinity. Okay, these are the two terms that are usually confused when it is asked to define what is this ionization energy. You can say here, it is the minimum amount of energy required to remove electron from isolated gaseous atom, and the opposite of that is electron affinity. It is amount of energy that is liberated, okay, when you are trying to add a electron to the gaseous atom. So what is the difference? In ionization energy, you are basically giving the energy, okay, you require some energy to remove the electron. But in case of electron affinity, what happens is that your energy is liberated in the process. Okay, there you need energy, here energy is liberated. That is the difference. Now next is the types of quantum number that are the basic fundamental that has to be kept in mind while drawing the shapes of the orbital. There are basically four types of the quantum numbers. Okay, the first is that your principal quantum number, okay, that is denoted as your N. Then you have angular quantum number denoted as L, magnetic quantum number denoted as M, spin quantum number denoted as S. Okay, you can remember the relation how to calculate the quantum numbers. Okay, you have defined 4 types of quantum number, but you need to calculate the quantum numbers for the different orbitals. Remember the relation, your n value, that is principal quantum number, will be given to you. Okay, and from that you can find out the L, that is your angular quantum number, as n minus 1, and your M can take up value from plus L to minus L. Okay, remember this thing. And the spin quantum number can have plus half and minus half. Okay, value that depends on the pairing. Look here, we'll discuss the case for the s orbital. S orbital principal quantum number n is 1. So formula states this L equal to n minus 1. So we can write 1 minus 1 equal to 0. Then you have M. Okay, there plus L to minus L. So you can write here your L value is 0. So straight away your M value will come out to be 0. And your s orbital is one-fold degenerate. Why it is one-fold degenerate? Because your magnetic quantum number is having only one value, that is 0, and your shape of the s orbital is spherical. Okay, and hence s orbitals can take up 2 electrons. For the case of the p orbital, very clearly it is stated that n value, that is principal quantum number, is 2. So L value will come out to 2 minus 1, that is 1, and M will take up the value from plus L to minus L. So M will be equal to plus 1, 0 and minus 1. So it means your p orbital is 3-fold degenerate. Okay, so it can take up maximum 6 electrons. For the d orbitals, you can see here your n case is 3, so L equal to 2. Then you can write down M equal to plus 2, plus 1, 0, minus 1, minus 2. So d orbital is 5-fold degenerate. The shape is complex and it can take up maximum in the 10 electrons. For the f orbital, the case is very simple. The quantum number principle states that n equal to 4 value. L can be given as equal to 4 minus 1, 3. M can take up value from plus L to minus L. So you can see here total M can take up the 7 values, and hence your f orbital is having 7-fold degeneracy. The shape again is complex and can take up 14 electrons into the orbital. Look here, the shape of the p orbital, that is, the p orbital is basically having the dumbbell shape. Whenever you are drawing your px orbital, you can draw something related to the graph system. Okay, there is a x-axis, there is y-axis just like graph, and there is a z-axis. For px, your dumbbell should lie on the x-axis. Okay, for py, your dumbbell should lie on the y-axis, and for pz, your dumbbell should lie on the z-axis. Just a brief